So on our Unit 10 stoichiometry notes, the first part says when we use stoichiometry, which is really just to tell us how much product will be made or produced, or how much reactant is used up in order to make a product. And then part B here says that coefficients in a balanced chemical equation can tell us a number of things. So 1 is the number of individual particles of each thing in the reaction. 2 is the number of moles of particles. And then the third thing is that we can use the mass of the reactants with the molar mass of the compounds to figure out the total mass of each thing in our equation. So I actually want to jump down a little bit to remind us of what moles are. Does anyone remember from our last semester how we define moles or how we used moles? Okay, yeah, in an equation. We're close. Okay, so first, a mole, we're going to abbreviate it as MOL. And a mole is represented by Avogadro's number, so I think that's what y'all are getting at. Avogadro's number so 1 mole is equal to 6.02 times 10 to the 23rd things. I'm going to put that in quotes because obviously things is not a scientific term. But yes, 6.02 times 10 to the 23rd things, particles, atoms, molecules, whatever it is. So we use the term mole similar to how dozen is used in other contexts. So for example, if I said I wanted 1 dozen students, how many students do I want? 12 students. If I said I need a dozen eggs, that means how many eggs? 12 eggs. If I said I need 1 dozen molecules, how many molecules do I want? Moles works the exact same way. So if I say I want a mole of anything, that's why I put things here. I know that's not specific. But if I said I want a mole of students, that tells me I want this many students. So the reason that we use this and the reason it's such a big number is because typically it is used for molecules or tiny, tiny particles, atoms, ions, formula units, that kind of thing. And so we need a lot of them to actually get a measurable amount. But the phrase a mole is used the exact same way that we would use a dozen. So that is the actual number, okay? So we use this to tell us the amount of a substance. So this is the SI unit for the amount of a substance. And then the other thing I want us to write is actually what this number represents. So 6.02 times 10 to the 23rd. Since it's been a while since we've used anything with scientific notation, that's how we call that format of number. Times 10 to the 23rd, since that is a positive exponent, that means you are multiplying this number, 6.02, times a really, really big number, or what you're doing is you're moving the decimal place 23 times to make this number bigger. And so when I teach scientific notation, I always teach you're moving the decimal to make the number bigger, or you're moving the number to make the decimal smaller. I never teach left and right because, first of all, a lot of you mix that up. But second of all, it depends on if you're going into scientific notation or taking it out of scientific notation, and then it gets flipped and you get even more confused. So this is going to be a really, really, really big number. So if you're trying to determine which way you're moving your decimal, if I move it in this direction, that's going to make my number smaller, so we actually want to move it in the other direction. So what I'm going to do is I'm going to get this out of the way. No, I'm not. I'm going to keep that there. Times 10 to the 23rd, so we'll put that there. Okay, that is equivalent to 6.02, and then I want you to have space to move your decimal 23 times. So if I move it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. So that is where your decimal would end up. And then in each of these little divots, give yourself a 0. And then I'm going to erase that just so it looks a little cleaner. And then the decimal's gone there. So if I go 1, 2, 3, comma, 1, 2, 3, comma, 1, 2, 3, comma, 1, 2, 3, comma, you have 3, 6, 9, 12, 15, 18, 21 zeros tacked onto the end. So when I grade your notes, I'm going to look for this number written on there. So take this time to actually write it out. So when I say that 1 mole is equivalent to this many things, typically, instead of things, we're going to use what we call representative particles. These are the things that we're usually counting in this mole quantity. And while we could count, again, similar if we relate this to a dozen, typically when we talk about a dozen, we think of things like eggs. You count a dozen eggs, or a dozen donuts, or a dozen, honestly, I don't even know anything else that has a dozen. Eggs, donuts, bagels, maybe.
Never heard of a dozen bagels.
A dozen bagels? That's common.
Sound bad. I never heard that before.
Yeah. But like a dozen students, that just is like kind of random. Like we don't often use it for that, but you could. It would still mean the same thing. Similar to that, a mole, we are typically talking about a mole of molecules, or a mole of formula units, or a mole of atoms, or something like that. I could say a mole of students, but it just kind of is like not the right context. It still means the same thing, it's just not how we typically use it. So when I say things, I'm usually talking about representative particles. So here I have an atom. On your periodic table at the top, you should have a basic definition for atom, which is just what?
Any single element.
Any single element. So an atom is going to be any single element. So I could have a mole of atoms, or a mole of anything that is a single element. So if I go back up here, this would be called an atom. Or if it's going to have a charge, then I would call it an ion. Then a molecule. Remember, we abbreviate molecule as MC. Molecule is a covalent compound. What does covalent mean? Or what type of compound would be covalent? 2 nonmetals, perfect. So nonmetals only. And then a formula unit. I abbreviate this one as what? If you're not sure, you should already have this written on your periodic tables. I don't know why this is glitching. Do you see it scooting?
Yep.
I don't know why it's doing that. That's weird. Oh well. Try again. Okay. So formula unit, we abbreviate that as FUN. A formula unit is another compound, but instead of it being covalent this time, this is any ionic compound. So this is always going to be made up of a cation and an anion. This is when you crisscross their charges. And then this will come up a little bit later, but I guess I kind of want to include it in the notes now, is that a molecule, this will break down into atoms, meaning this breaks down into single elements without a charge. And then a formula unit, this one will break down into ions. I'll make that cleaner. So the only difference being that an ion has a charge because they are ionic compounds. So if I want to keep going on this. We'll finish the bottom part and then we'll kind of jump back up to the top. I put this little square on here so that we can copy an element from your periodic table. So looking at your periodic table, do you have a specific element you want to make this for? Gold. All right, so gold on your periodic table is right here. So I want us to copy this element square onto the square that's in your notes. So we're going to write 79 and then AU and 196.97. 196. Okay, so gold is element number 79, and it is AU, and I forgot what order. Okay, 196.97, and it says gold. I'll make the AU bigger. So each of our element squares are set up this way, but I wanted you to have this in your notes. This is your atomic number. When have we used this before?
Proton.
Number of protons, good. So this will always match the number of protons. If you have an atom, that means your number of protons equals your number of electrons, and if it's an ion, you still have that same number of protons, but your number of electrons changes. That's how you end up with your oxidation numbers, the charges that we write above our periodic table normally. This is what we call the symbol. So when I say element symbol, that's what I'm talking about. It's like the abbreviation for the element. You don't get to make up your own symbols for these. They are given to you on your periodic table. So one that I see all the time is if I say potassium, a student will write P because they think potassium can be abbreviated as P, but P is a different element, so don't call it that. And then this number down here is really where we're going to focus in this unit. This is multiple things. One of the ways that we have called this before is your average atomic mass, but in this unit we are going to use it as your molar mass. So if you have learned that that is the average atomic mass or the atomic mass before, that's not incorrect, but it is also representative of the molar mass. And then, of course, this down here is just the name. So your molar mass, what I want you to have on your paper is a definition for this. Do you remember learning about molar mass last semester? All right, molar mass, if you don't remember, is just the mass. I'm going to put specifically in grams of 1 mole of a substance. The mass in grams of 1 mole of a substance. What's important about using molar mass is that it is always going to be specific to the exact substance. So for example, if I had 1 mole of gold, let's use this as our example, 196.97 is our molar mass. So 1 mole of gold, AU, is equal to 196.97 grams. Is this starting to look a little bit familiar? Okay. So 1 mole of gold weighs that much. That is why it is called the molar mass. The way that we'll usually write it is with the units of grams per mole like this. So if I had a question on your test, for example, that said, what is the molar mass of, let's say, I don't know, oxygen. What you would write is you would look up oxygen on your periodic table, and I see oxygen up here has a molar mass of 15.999, so the correct answer, if you were answering that question, would be 15.999, and then the unit you would use on that is this, grams per mole. So typically, if we are asking for just molar mass, this is what I am asking for, grams per mole. I can't just ask what is the molar mass if I don't tell you what substance it is that I'm talking about. I'm going to zoom in here just to give myself more space to write. You don't necessarily have to write this, but I think it might help if you do. So if I said that you were driving on the highway at, say, 90 miles per hour. This is so that we're familiar with this unit. Okay, so 90 miles per hour. Another way that you can write that is 90 miles per 1 hour. Right, 90 miles per hour. That's not typically how we see it. We usually write it as mph, but this means the exact same thing, right? Nods? Okay. If I were to ask you, okay, if you drove for 1 hour, how many miles did you go? 90. You don't have to do any math to figure this out. It is just about reading that ratio. If I tell you that you drove 90 miles, how long did that take you?
1 hour.
1 hour. So you see, you can write it, and it gives you the same information either way. It just depends on how you ask the question or what the given information is. But all of that comes from the same thing, 90 miles per hour. So I like to relate that to this part because really what's happening is if I have 1 mole of oxygen, it's going to weigh 15.999 grams. Remember that we are not going to round anything from your periodic table. So when you calculate the molar mass of something or when you look at your periodic table to get that mass, you're going to keep all of the decimals that are provided for you, which is also why it's important that you're using my periodic table that I give to you during class and not one from online, their masses might be slightly different. Like they're going to be the same general mass, but they sometimes round to different decimal places, and I want your mass to match ours exactly. And so the other ways that we write this, often we will see it as grams over 1 mole, or 1 mole is equivalent to a certain number of grams, just like here. Miles per hour tells me 1 hour, I want 90 miles. Or if I want 90 miles, I drove for 1 hour. So we use it the exact same way in molar mass. The important thing to remember here is that molar mass is always 1 mole. Just 1. And then as a reminder for molar mass under elements and compounds, if I have an element, we find the molar mass just like we did up here. So for something like hydrogen, so molar mass of hydrogen as just H. To find that molar mass, I would look at my periodic table. Hydrogen is up here, so its molar mass, 1.008, would be 1.008 grams per mole. But hydrogen is one of those elements that we call diatomic. Remember your Brinkelhoff elements, Br, I, N, Cl, H, O, and F. All of these elements don't usually exist on their own like that. Usually, if we were asking for the molar mass of hydrogen, it would be H2 because it is diatomic. So any of these guys would have a 2 on them, which means I need to multiply that mass by 2. So instead of your mass just being 1.008 grams per mole, I would multiply that number times 2, so it would be 2.016 grams per mole. You see the difference?
Yes, ma'am.
Okay. And then if I took this one step further, and I made an actual compound with this, I could take like H2O, molar mass of H2O. I'm going to put that like, I would take hydrogen times 2, since I have 2 of them, and oxygen times 1, since I only have 1 of them. The molar mass of hydrogen, again, just comes from my periodic table, so it's still 1.008. But when I multiply it by 2, this is what I get. And then I have oxygen. I only have 1 of them. So oxygen we already looked at, 15.999. And then to figure out the molar mass of this entire compound, I add them together. So 15.999 plus 2.016. If you can't do that in your head, you need a calculator. So reach around, there are calculators sitting on the desks. Grab whatever calculator, type this in, and calculate it for yourself. 2.016 plus 15.999. Of course, it's okay if you want to do like long addition, that's fine. But some of these get pretty long and difficult, so definitely calculators. All right, if you have added these two numbers together, what did you get? 18.015. And our unit on that, since it is molar mass, is what?
Grams divided by mole.
Good, grams per mole. So far, so good? Alrighty. Let's scroll back up to the box that I skipped. So all of that was kind of like refresher background. We learned this all last semester. So if this looks familiar, it's because we did it in the fall, but it's been a while since we've done anything with math. If you did not take that minute to go grab a calculator, do so now. You're going to need a calculator. So then up here, where we have this equation, I have iron reacting with oxygen to form Fe2O3, which is the formula for rust. I want us to balance the equation. And even if you can balance this in your head, I want you to have a reactants and products chart for this one specifically. So reactants and products. In my equation, I have iron and oxygen. On my reactant side, I have just one atom currently of iron, and I have 2 atoms of oxygen. And on my product side, I have 2 atoms of iron and 3 oxygen. So to start, what coefficient would help me and where? Bless you.
Thank you.
2 here?
Iron and
Oh, Fe2O3?
Yeah.
Okay, so 2 right here in front of Fe2O3. 2 times these 2 iron gives me 4, and then 2 times the 3 oxygen gives me 6. So on my product side, I have 4 iron and 6 oxygen. On my reactant side, none of them are balanced. So what coefficients could help me and where?
4.
Where?
With Fe.
Okay, 4 in front of Fe, so 4 times 1 iron. And then?
30 for oxygen.
Perfect. Oops. And that gives me 6. So what this shows me is that I have the exact same, once you finish balancing, you have the exact same number of each type of atom on each side of your equation. I have a total of 4 irons and 6 oxygens on my reactant side, and I have a total of 4 irons and 6 oxygen on my product side. Since I have the exact same number and type of atoms, Mackenzie, put your phone up. Since I have the same number and types of atoms on each side of the equation, the weights are going to be the same on the reactants and on the product side. So if I were to count this, I can use my coefficients to tell me the number of individual particles and the number of moles of particles. So what that means is that if I say my coefficient is 4 in front of iron, that means I have 4 ions, or 4 atoms really, of iron. I called it ions because it's going to end up making an ionic compound, but as it stands, this would really just be an atom. For every 4 atoms of iron that I used, I'm also going to use 3 molecules of O2. My 3's keep being weird. And that is going to produce 2 formula units of Fe2O3. So for every 3 irons, you get, for every 4 irons, 3 molecules of oxygen and 2 Fe2O3s. We can use those same numbers for the number of moles of something. So 4 moles of iron would need to react with 3 moles of O2 to produce 2 moles of Fe2O3. And then the number of grams is going to be different because here we actually have to use the molar mass of the substance and then multiply it by how many moles there are in the equation. So for each of these, all we did was use the coefficients, but now for grams, we have to do it a little bit differently. So that's why I kind of jumped down and reviewed molar mass for us. So for grams of iron, if I'm looking at my periodic table, the molar mass of iron is 55.845. So I'm going to type that into my calculator, 55.845. This is the molar mass, which tells me that 1 mole of iron is equal to 55.845 grams. But according to my equation, I don't have 1 mole of iron, I have 4 moles of iron. So what do I need to do to that number? Perfect. So I multiply that by 4, and that tells me the total mass of iron that I have on my reactant side of the equation. So typing that into your own calculators, what did you come up with? 223.38. Good. Then if I move on to O2, if I wanted the mass of O2, or the molar mass of O2, oxygen is 15.999, which means that 1 mole of O is equal to 15.999 grams. But in this equation, it's not just O, it's O2. So if I had 1 mole of O2, the difference would be I would multiply that by 2. So just like how we did the molar mass of hydrogen at the bottom, because it is diatomic, we have to multiply it by 2. So 1 mole of O2 is going to be 15.999 times 2, which is what? 31.998 grams per 1 mole of O2. You with me? Okay, so 31.998 grams per 1 mole of O2, but again, in my equation up here, I don't just have 1 mole, but I actually have 3 moles of O2. So I'm going to take that 31.998 and multiply it by 3. And I end up with 95.994. Effectively, what you did is you multiplied the 3 times 2 so that you had 6 total atoms of oxygen, which is what we had in our reactants and products chart. We said we had 6 atoms of oxygen. So if I took 6 times 15 times 15.999, that would have given me the exact same number. So that's the total mass of oxygen on your reactant side. And then on my product side of the equation, I have Fe2O3. So I'm going to take the molar mass of this. So I'm going to use a different color and write it up here. So Fe2O3, molar mass of that. I would take my iron and my oxygen. I have 2 iron atoms and 3 oxygen atoms. And we're just going to multiply each of those by their molar masses on the periodic table. So iron is 55.845. And oxygen is 15.999. So there are a couple ways you can do this. I put the equal sign so that you can get these, and then you would add those together if you do it separately. I tend to like to use parentheses. So when I type this into my calculator, what I actually type is this plus this, and I don't hit enter in between. So if you want to follow along like that. So I'm typing open parentheses 2 times 55.845, close your parentheses, plus open parentheses 3 times 15.999, and then close your parentheses. If you don't use parentheses, if you're not a fan of putting it all in together, of course you can still get the answer by taking it this way. So when I did that, I got 159.687. Is that what you got?
Yes, ma'am.
Perfect. If I make a mistake, let me know. So this tells me that 1 mole of Fe2O3 is equal to that many grams of Fe2O3. However, I don't have 1 mole, I have 2 moles, so I need to double that number. I need to know that 2 moles of Fe2O3 would just mean that I'm multiplying this by 2. So 159.687 times 2 equals 319.3 3.74. Since that Fe2O3 is the only product in this equation, that means that this mass of that product is the total mass of all of the products on that side. So since this is the total mass of that entire thing, that is the entire mass of all of your products. So you can just copy that number, 319.374, down to the mass of all of your products. I know that the law of conservation of mass tells me that the mass of all of my reactants should equal the exact same thing, but we can prove that by taking these two numbers that we calculated, the 223.38 plus 95.994. Add those two together, and it should, if we did everything correctly, end up being the exact same number. So 223.38 plus 95.994. And does it come out to the same thing?
Yes, ma'am.
Yes, of course. 319.374. Good? Both of these numbers, so the 319.374 that we got on each side, we could have also gotten by taking 4 times the molar mass of iron plus 6 times the molar mass of oxygen. This is just showing that when you have the same number of atoms of each type on each side of the equation, it's going to weigh the same amount on both sides.